Hi all, welcome to another session of S3 Skills. Today we are doing a deep dive topic, and Abhilash should be presenting Elasticsearch today. And with this, I would give the podium to Abhilash. Over to you.
Hello, everyone. So today we'll have some agenda. We'll go through the basics of Elasticsearch. What are the different applications of Elasticsearch? And we'll also get to try out some queries on Elasticsearch. So we'll have a quick demo in the end. Feel free to ask any questions anytime in the middle, or feel free to post them in the chat. And we'll make sure that we understand each of the specific pieces before moving forward. So if you've heard about the ELK stack, where E stands for Elasticsearch, L stands for Logstash, and K stands for Kibana. So it's a very well-known stack that is used for log management and analytics in various organizations. There are thousands of organizations that currently use it. So let me start with this. So this is one of the applications of Elasticsearch, although it's used in other places, but this is one of the common applications that we'll start with. So we have an idea of how it is used before we actually deep dive into the specifics concepts. So Logstash is a tool which is used for data aggregation and processing. So we have a data coming from a lot of different sources, like each application that is running, each server that is running, each process that is running. They're all generating logs, and we might have like hundreds or millions of such log entries depending on the application, how big our application is, uh, and how widespread it is. And these may be coming from different sources. So we may have application instances across the world, and we may still want to aggregate all these logs, perform some kind of transformation on them, and then store them somewhere. So the aggregation and processing part is what Logstash handles. And once we've collected all this data, this is stored, this needs to be stored somewhere. So Elasticsearch acts as a storage mechanism. Basically, it provides storage for all these logs, and then it also indexes those logs so we can query them later. Now, Kibana can be used to actually analyze the log data that has been stored in Elasticsearch. And then it allows you to run queries and quickly search any data that has been stored. And then you can also build dashboards to visualize that data. So any questions so far on what each of these components is?
So Logstash is specifically for only log data aggregation processing, right?
Yes. So Logstash has a lot of plugins, like input plugins and output plugins. So what it's saying is it's retrieving data from a lot of sources. It's mostly log data, or it could be any data um, coming from different sources. And it does some kind of aggregation on them, like and it enriches that data, and you can define filters, and you can define some rules as to how that data is processed or enriched. And then it has output plugins, and it can actually store that data somewhere else. And this part is applicable for logs as well as any other data that you may want to transfer. It's generally like text data coming from different sources that you want to aggregate. Um, but yeah, it's generally for logs, but it could be anything other than logs as well.
And is this data aggregation real time, or it runs as a batch process?
Yeah, good question. So this entire pipeline is near real time. So within milliseconds or to seconds, the data will actually propagate to Elasticsearch and be available for query.
And Kibana and Splunk both are the same, or it is a different?
So this ELK stack is one of the popular ways for managing and analyzing logs, and Splunk is another one, but they are completely separate from each other. ELK is open source, and Splunk is owned by a private organization, and it's not free. But they both serve the
So
same purpose.
Splunk actually, yeah, Splunk also does actually the same purpose of what, if you don't want to buy a public property, public component, then you can use this. And Logstash can also be used for document management if you want to search PDFs or something like that. That's what we do in our team.
We use Grafana instead of Splunk in my previous companies, so that's for alternative. Yeah.
Grafana is just for visualization and a little bit of data processing, similar to Kibana.
Oh.
And does it guarantee the delivery of data, or there can be data loss also?
So this is pretty reliable, but I wouldn't say this is 100% reliable. So it is possible that you search for something and it may not show up because something went wrong. But in most cases, it's reliable. All that data would be there.
Yeah, is there like any expiry, like the data can expire, like, or how long the data can persist?
So this needs to be managed by the mechanism in which we use to actually push data. So let's say we can have one index in Elasticsearch for each day's worth of data, and then we can clean up the older ones when we don't need them anymore.
Okay, so those configurations can be done. Okay,
yeah.
Thanks.
Yeah, you own the cleanup of how much ever you want, 6 months, 1 year, or 2 years. But the performance may vary.
Right. Yeah. And in this stack, the Elasticsearch is at the heart of the stack, and it's the component which is not optional. The other components are optional. So you may choose not to use Logstash at all, and you may have some other mechanisms to push that data to Elasticsearch. So let's say there are lots of different agents available that you can install on the servers, and then they may directly push data to Elasticsearch. And for analysis, you may choose to use the Elasticsearch APIs directly and not through Kibana. And then you could use other tools like Grafana for like building the dashboards. So Logstash and Kibana are optional parts of it, and Elasticsearch is the core part, like which is making the search and indexing, which is handling all the indexing part and making searches simpler. So one of the recent additions to the ELK stack is Beats. It's another component which has been added to it recently, and it's basically an agent that can be installed on servers, and it's going to do the job of taking the logs from different sources, like on the server. Let's say you have 5 different processes running on a host. It will, and you can specify the log location for each of those 5 processes, and then it's going to monitor changes in those logs and push them to Logstash. And for larger organizations, when there are a large volume of logs generated, in that case, we might need to add additional components to our architecture. So this is an example of the ELK stack architecture when there's a large amount of data. Think of like terabytes or petabytes of data. So Beats is the component which is actually handling the data collection. It has a config file where I can define all the paths to all the log files that need to be shipped and stored in Elasticsearch. And it constantly checks any updates made to those log files, and it basically propagates those updates to a message queue, so let's say in this case we use Kafka for buffering the messages, because there are a large amount of messages generated, and we may not be able to process all of them at once and Logstash. So what we are doing is we are buffering these messages in a messaging queue, and then we are limiting the rate at which Logstash is processing it, which is as expected, because Logstash has previously had a lot of issues processing large amounts of data. Some data gets missed. So this buffering mechanism allows us to handle that in a graceful way. And the rest of the stack is still the same. Any questions so far?
So I have a question. So in this case, Beats is really a sort of like a plugin or some sort of library that you use in your application that constantly, pushes the data depending on your size of the log and the things that you want to, stream through Kafka to Logstash. So is that how the Beats is configured basically in the application?
So Beats is separate from your application. So you wrote your application to generate logs and write it to a file on the file system. You could use any logging library for it. So that part still remains unchanged. So Beats is completely isolated. So now you may have 5 applications running on, let's say, one instance of the host, like one VM. Then there will only be one instance of Beats on that VM. So it's basically think of it as a daemon that is installed, and an agent that is running on that VM, and that VM may have 5 different applications generating logs to 5 different files on the file system. Now Beats is looking at all those 5 different files, and any changes that are happening to those files, it's propagating messages to Kafka for each of those changes.
I see. And how does the Logstash?
All the Beats.
Yeah, please go ahead.
How do we know if all the Beats agents are sending the data, or if any Beats agents are down, or if there are any new instances added to application server? How do we know if the Beats agent even in those new application instances are sending the data?
Right. So that needs to be handled outside of the stack. So we need to have some kind of monitors that track of logs from each of those instances. It's possible to do it by querying the Elasticsearch as well. Like if we know from a separate source that, okay, these are the 100 instances we have, but we only have logs from these instances in the last 1 hour. So we can alert based on that as well. But yeah, it all happens outside the stack. I guess there was another question.
Yeah, so I think I was wondering about the Logstash. So are you going to cover a little deep about how the Logstash is configured and how it is run actually? Are you going to kind of talk about that in the next few slides? Then I can wait.
So I think we'll only have time to cover Elasticsearch because it's like a large topic in itself. But if you have any questions, I think we can discuss them right now.
Okay, so I was actually wondering about just to get the sense of Logstash, because I mean, again, I'm actually throwing out idea here, but I have also heard similar thing called Fluentd, and I don't know, like I've used, I mean, I haven't actually used none of them, but I was wondering if when you don't use Logstash and when you use Fluentd in some cases.
So Fluentd is a log collector. So it's similar to Beats. You install it on a host machine, and it's going to ship the logs for you. Now Logstash is basically receiving logs. It could be receiving logs from hundreds of sources. In case of Fluentd, you need one instance of Fluentd on each of the servers, and then it's basically just sending those logs from that one instance. Logstash is aggregating data from like all the sources, like all your host instances. So you could replace beats by Fluentd, and then each of the Fluentd instances is actually pushing data to Logstash. So you could have that.
I see. Makes sense.
I got one question here. So you mentioned that Beats was recently introduced into the stack, right? So before Beats, how do you collect the data? Which like what was a part that was helpful to collect the data?
Yeah, so you use agents like Fluentd or any other agents. There are a lot of them out there, and you would use one of those agents to actually push the data.
Got it.
All right, so let's jump into Elasticsearch now. So Elasticsearch is a full text search and analytics engine, and it's based on the Apache Lucene search engine library. So Apache Lucene is basically a search engine library which provides like scalable and high performance indexing. Like it has a lot of search algorithms built in that make queries like complex queries very easy and quick to compute. It's distributed. Uh, so basically, your data is stored in a distributed fashion across multiple nodes, and it's highly available. Like even if one of the nodes goes down, your data would still be accessible, and it's very scalable. Like even if your data is huge and doesn't fit one of the host machines, you can scale it horizontally across uh, a large number of nodes. It's open source, so you can actually go to GitHub and check the source code. It's developed in Java, and it has a very extensive REST API to handle the data and the cluster management as well. Any questions on this? Any terms that are unclear?
Yes, so like if the data is like dynamic and it's like changing very frequently, so then how does it maintains the consistency like sort of in the search?
So consistency. Okay, so this Elasticsearch doesn't provide asset guarantees, and the data stored in Elasticsearch is eventually consistent. So if you make an update and immediately make a read, it's possible you won't see that update. So this is the expectation that it might take some time for the updates to propagate.
Okay, sure.
So Elasticsearch is basically a document-based NoSQL database. So if you're familiar with other NoSQL databases that store documents, then you could compare them to Elasticsearch. The difference here is that it's doing a lot of indexing. It's using the Apache Lucene search library to do a lot of indexing on that data, so you can perform all those complex queries.
So Lucene is
Sure,
only
sure.
used for indexing purposes.
Sorry?
Purpose of using Apache Lucene is for indexing, improving the indexing and all, or is there anything else?
Yeah, so Lucene is the major like core feature of Elasticsearch. Like we want to compute indexes which are different from like the indexes that traditional databases provide. So let's say if I have another NoSQL database like DynamoDB or Cosmos DB, then I can add indexes on each of the fields or a combination of the fields, and they would be something like, okay, get me all of the documents where this specific field has the specific value. But it doesn't allow me to perform complex queries. So I can't say that give me all the fields where this specific field let's say matches this specific regex or basically regular expression, or it doesn't allow me to say that, okay, I don't know the field that I want to search for, I just know the term that I want to search for, find it in all the fields. So I don't have an index like that in like typical NoSQL databases. So when I use Apache Lucene search library, it indexes all the data in such a way that all these complex queries that I can think of, some of the ones that I just shared, they are much simpler. They are already indexed and they can be queried in milliseconds.
Okay.
Okay. Any more questions? Any terms that are unclear on this slide?
Can you give the sample of queries that are that you were talking about? I think I missed it in the last part.
Yeah, so it could be queries like I just know of a specific part of a substring of text stored in the document. I don't know which field's value it corresponds to. I could just search there. So let's say I want to search the string error anywhere. I don't know if it's in the message field or it could be in some log message field or some any other field. I just want to search all documents that contain the string error. Or I have a regular expression I want to search for, and it could be anywhere in the document. And like if you want to do some kind of such queries in traditional NoSQL databases, you won't have indexes that will help you with those. But using the Apache Lucene library, we are able to perform those queries because it indexes it to allow all of those queries. We'll also go through some specific examples and actually a demo of some of the queries. So maybe that will help as well.
Okay, thanks.
Okay, so if all of these terms are clear, then we can actually move ahead. Let's go through the use cases. So one of the common use cases is in search engines. So let's say I have a lot of documents. I want to make them searchable. I could do that. Let's say I'm a e-commerce website. I have millions of products. How do I make them quickly searchable? So I could use Elasticsearch for that. So I have lots of, let's say I'm a news website and there are lots of articles that are being posted and I want to allow people to like search across those articles. Then again, it could be used similarly for like messages, lots of messages being handled, if there are blog posts, or if it's just a big search on like all the users. It basically the Lucene library is handling indexing in a way that makes Elasticsearch good for search engine applications. So just in this use case, I'm sure you'll be able to relate it to a lot of system design problems where Elasticsearch could be used. Then the second use case is for logging and log analytics. This is the one we actually started with initially. We can ingest a large amount of log data and then be able to analyze that data in near real time. And we can also use it for business and security analytics, like given that the data is near real time, we can perform lots of queries like aggregation. We can get the count of data, we can group data by a certain field, we can summarize data in different ways. So it can be used to make like business decisions as well. Another use case is auto completion and instant search. So let's say I type something and while I'm typing, I want to see like what are the documents or like blogs or messages or products that match. Like, so this can be used for auto completion and quickly provide me the results that match. And if I, let's say, while I'm typing a word, if I type an additional character, then it can actually completely fetch quickly fetch the new results that match that string and update the results available. Compare, you could compare it to, let's say, how a search engine works in Google, or let's say these are just some kind of search you're performing on an existing website. It could be any other website, and you could be searching for let's say anything. It provides the auto completion capability. And you could also perform fuzzy searching. So you typed something, but you misspelled it, and you want to find out what are the, like, say, the nearest neighbors or the closest terms that uh, relate to what I just typed, and find out, like, fetch the results for those. So it could help point out spell check errors as well. It could automatically help with finding the related documents, even if, let's say, one of the terms is incorrectly spelled. Any questions on these use cases?
Quick question on the ranking. So,
Yeah.
is it possible to use any personalized signals to like get the ranked results? Because I see that it may be using something TF, IDF, or a better version of that to find the right documents. But is there any way in which you can, maybe send signals that the user has been interacting with this pages, so they should get more priority in the results, or this was the recently accessed page, hence prioritize that more in the ranked results or something like that?
Yeah, so this out of the box, it won't help with the ranking in general. There's some component related to ranking. Let's say if we are using fuzzy search. Uh, so what it does, it uses the Lucene library, and the Lucene library can be used to also assign a score to how good of a match it is. So let's say I find 100 documents that match, that fuzzy match my query. But some documents are much closer, but other documents are like not much closer. So it assigns a score to each of those, like how good of a match each document is, which could be used for ranking in a way, but it doesn't have the business intelligence of, like, hey, the user actually previously clicked on this, and like, so that logic needs to be built on top of it at the application layer. But Elasticsearch would only use the Lucene library to rank the documents.
Got it. Thanks.
Any other questions on the applications? I know these are a lot. Like, if you have some other places you've seen it being used, feel free to share as well. All right. So there are thousands of companies that actually use it. This is just a very small subset. And we can pick a few companies and just like discuss like how they might be using it. So let's say we pick GitHub here. So on GitHub, if you go and search for some code snippets and repositories, you can see there are like a large number of repositories and lots of code, lines of code, but we are able to quickly retrieve results. So this is being powered by Elasticsearch. So all of these, all of the code, all of the files, all of the lines of code, they are already indexed. And when we make a search query, this goes to Elasticsearch, and it's able to quickly retrieve the results matching the query. And the query could be very complex as well. It could say that, okay, where this is the specific file name, and this is the specific term that I'm searching for. And all of those are actually translated to Elasticsearch queries, and then it's able to quickly fetch the results within milliseconds. Another example we could pick is, let's say, Stack Overflow. On Stack Overflow, every post that is added and every response to that post is indexed. And so anytime I search for a question, it forms the Elasticsearch query and then fetches the matching results. And it could search not just in the content of the message, it could also search in the metadata. Like if I have tagged a post with a specific tag in Stack Overflow, then yeah, it could search within those as well and apply those filters. Okay, let's pick another example. Let's say Slack. For those who have used Slack, it supports a lot of ways to search. Like you can search messages from a specific person. You can search for specific terms. You could just type random specific terms. And like, so all of these search parameters, although you specify them in the way the Slack query works, like you're following the schema of like the syntax of what Slack supports, but internally, again, it's being translated to Elasticsearch queries, and it's able to quickly retrieve the results because it's all indexed. Any questions on this so far, or any other company you'd like to talk about as to how it might use Elasticsearch?
Can you talk a little bit about how autocomplete might work?
Yeah. So with autocomplete, you have partial query, right? So you have the initial few characters of the query. So what Elasticsearch is doing behind the scenes is it already has a prefix tree built in for prefix matches. So anytime you, let's say, type the first few characters, so let's say you're searching for Instacart and you typed Insta, then it already knows what are the possible other words that could complete that partial word. It's already part of that index. So this is one of the uh, pre-computation that the Lucene library would allow us to do to be able to make prefix matches faster. So auto-completion is just prefix matches. And the Lucene library allows us much more complex matches in the sense that if instead of Insta, I misspelled a character, uh, even then it should be able to find that, okay, this is probably misspelled because I have a lot of other results which match this prefix. Does that answer your question? Okay.
Yes, thank you.
Okay, so let's look at the basic concepts in Elasticsearch. So we'll quickly go through these since we have limited time left. So we have a document which is just a JSON object, like storing a collection of key value pairs. So and each of the values can also be complex objects in themselves, but overall a document is just a full JSON object in itself. And this is comparable to if you're familiar with relational database management systems, you could compare this to a row in a table. So if you look at a row, let's say I have a users table, and I have a row which will have the values corresponding to each of the columns. So let's say I have a user ID, I have a username, user address. So in this document, this would be one document corresponding to that one row. So it will have user ID as, let's say, 1, username, and then user address, and so on, as different fields within that JSON document. Now, type is just a field within the document. It is used to like differentiate the different types of documents. So let's say I have a user document. I might have a product document, like, or let's say if I'm managing products and then users can buy products. So I might have product documents and user documents. So type is just a field. So the document will have a field whose name is underscore type, and then it will help make queries easier. So I can query based on, okay, only search on documents of this specific type. So it will automatically add the filter. So the type field is being deprecated in the future versions of Elasticsearch. since you can see that, okay, it's just another field and it can always be added to search manually. Then the next is index. So index is a logical partition of documents. So I might have 10,000 users. So I will have one document per user, which is 10,000 documents. But I may not want to store all of those documents at one place. But these are all documents of the same type. And I want to query them together. So if I'm querying for users, I want to query across all of those users. So index is a logical partition of documents. So I could have an index for, let's say, a user index. So whenever I want to query users, it queries all users. I could have a product index. So whenever I want to query products, the search is done across all of the products that exist, no matter how they are distributed. So index is just a logical partition of documents. So as you can see, like once we deprecate type, then again, we'll rely on index, because we'll only have all documents within an index basically would be of the same type. Only one type will be supported by any index in the recent versions. Then there's a concept called mapping. So with mapping, what we are doing is we are defining the different fields in the document. So let's say the document we talked about was the user document. It had fields like user ID, username. So in this mapping, we can define that, okay, user ID is UUID, and username is actually a string. So we can actually define the types for each of the fields here. And this is optional. So Elasticsearch is a schema-less database. We don't necessarily need to have a schema similar to many other traditional NoSQL databases. But what this mapping helps with, it provides additional data to Elasticsearch so it can index it more effectively. So if I have, let's say, a numerical field, I can specify that, hey, this is actually an integer, and this will help Elasticsearch take better decisions as to how to index that data. Any questions on these so far?
So I have two questions. So the mapping here refers to like how we define a data type in the databases like SQL, right? Similar to.
Right. Yeah. So you just define what type, what are the fields you are expecting, and what are the types of those fields. Yeah, that's it. So it's a subset of those, the data definition part.
So the default would be a string or object kind of in this.
So Elasticsearch manages it on its own, like based on the data. So we don't need to worry about the defaults.
So another question is like, let's say index is not defined by a user, and I'm searching right now based on the user ID. I get the data. Next time I search by product ID, I must get the product data very fast, right? So how this index works? It's like generated on the fly, or it pre-computes the index before searching. Yeah.
Right. So index is a confusing term. So in case of relational databases, we think of like a table as the actual source of data, and then we have indexes that exist to help us query that data more effectively. In this case, index is different. In this case, index is comparable to a table. And this is the actual source of the data. It's not something which is helping us query the data. It's the actual source. So we can't query data outside of an index. I mean, we could search for across all indexes, but then this is the core entity. Compare it to a table. It's like, so how do you query the user data without the users table?
Yeah. Okay.
Yeah, so it's a confusing term, especially if you're coming from the relational database world, but yeah, consider it as a table.
Do you have one copy in that index and one copy in actual source of truth data?
So the index is the actual source of truth, and then we can have copies of these. So we'll go into like how this is actually stored.
Okay.
Okay, any more questions? Like, because these are the core concepts. Like if these are
So
unclear,
is
then it
index
would be hard.
also replicated? I mean, what if we lose the index?
Yeah, so we'll come to how index is stored. We will cover those in the future slides.
So can I have a document with different keys being part of same index?
Yes.
So,
So
for example,
an index may have very different documents with completely different fields. So you can have a product document and a user document in the same index. So Elasticsearch is not mandating any specific schema. It's schema-less. So you could store any JSON document.
Yeah, so can you explain the type field again and why it is deprecated in the coming releases?
Yeah, so type is just a field stored within the document. So let's say we talked about the use case where index can actually store any kind of document. So I might have a user document and a product document in the same index. Now, how do I differentiate between these? So let's say I want to say that I have users and product documents in the same index, but when I'm querying, I want to search only in the user documents. So I need some way to actually limit the subset, right? So I want to say my query should only go to the documents which are of type user, which are user documents, not to the product documents. So I use a field named _type in each of the documents. So user documents would have value for _type field as user, and product documents would have the value as product. So the type can be used as a filter to limit the index to the subset of documents of that type. So I can say if my index name is, let's say, catalog, and my type is user, so I can say, okay, only query documents within the catalog index which are of type users, and then it will filter out the documents in index to only the documents of type user, and then only perform the search query on those. And type is you can see it's actually optional, because I can always specify that, okay, I'm querying this index, and first I apply a filter on all fields that have the type as user, and then I can add other filters that I want. So you can see that like having the type is actually redundant, because I can always add it back to the query.
Okay, got it. Thanks.
Yeah. Okay, so a few more terms. The node. So node is a single running instance of Elasticsearch. A cluster is a collection of one or more nodes. And these nodes, okay, so these nodes, we could have one or more nodes running on the same physical or server or VM. We could have one or more nodes running on the same instance, but it's recommended to have one node. So we make sure that if one node, like just to make sure that there's high availability, and if that one VM goes down, like it's not affecting nodes where like the actual data as well as the replica data resides. But yeah, we'll cover those next. Cluster is just collection of one or more nodes, and these could be across different physical servers or VMs. Shard is a single Lucene index, and it helps provide scalability. So basically the index that we talked about in the previous slide, this index, which is the logical partition of documents, each index could have the data divided on multiple shards. So if you look at an index, there's no limit on the number of documents it can have. You can have millions and billions of documents that an index can have, but that data may not fit on one single node. So to be able to scale horizontally, we have the concept of shard, and a shard contains a subset of the data within an index. And each shard indexes the data for the documents, for the partial subset of documents that it's storing separately. So each shard is a single Lucene index. And if we want to, let's say, copy data in a shard, we have to copy the complete index. It's a single entity in itself. And it also helps with performance. So if I have 1,000,000 documents and I have 100 shards, each of those shards has, let's say, 10,000 documents, then I can perform queries across all of those shards in parallel. So it's actually helping me with performance as well. So if all of those 1,000,000 documents were on a single machine, then I would have to go through all of those 1,000,000 documents before I can return a query result. But in this case, it is let's say in our example, we have 100 shards and each shard has 10,000 documents. Now we can send the query to each of those 100 shards, and each of those shards only has to look at 10,000 documents. So they are able to compute the query result much more quickly. And then those results are aggregated and they can be returned. So it's helping with scalability as well, which is like horizontal scaling. And it's also helping with improving the query performance, because now the queries need to be performed only on a small subset of data, and the results can be combined from all of the different shards. And we
So
have
I have one confusion. The index is stored in the shard or the document is stored in the shard?
Okay, so index has lots of documents. Like think of, okay, one index, it's storing, let's say, 10,000 documents. Now shard has a subset of the documents within the index. So let's say I have 10 shards and each of the shards has 1,000 documents. Does that answer your question?
Okay, so shard has the documents. So where is my index stored?
Okay, so index, going back, it's a logical partition of documents. So it's just a logical entity. It's not a physical entity. Shards are a physical entity. They physically reside on a specific node.
So index is something we keep in memory.
So index is just a logical partition. Logical means it doesn't have a physical representation. It's just used to effectively query data. So index, consider it as a mapping of the index name with all of the shards. So when I execute a query on an index, it knows that this index is a collection of these n number of shards, and any queries executed on this index will need to combine the results from these n shards. So it's just a logical partition. There's nothing physically that exists for it. And a shard is actually a physical thing, like it's a Lucene index that is stored on a node.
When you say there is no physical and it's only a logical partition, that indirectly means it's in memory, right? Like you're not persisting it; it's kept in memory.
So the metadata still needs to be stored. So what the index name and the shards that correspond to it, this data still needs to be persisted.
If it's persisted, then it is a logical, like it's not logical, it's like actually persisted in DB. So you need to query the DB to find out like what index corresponds to which document.
Okay, so for each index name, we will store what are the corresponding shards that correspond to it. But we aren't storing the actual documents. So all those documents are only part of the shard. The actual documents don't exist in an index.
Sure, you're telling this the address, a metadata address of where the actual logical partition exists. That only that information is stored somewhere. That somewhere is in memory or somewhere is in like actual persisted data.
So you mean the mapping of index to shards?
Yes.
So that needs to be persisted because the cluster can actually restart, right? I mean, all your nodes could actually restart and you still want to retain that data. So it has to be persisted.
Exactly. So if you have a lot of such indexes, then how would you query is my question. Like you have to query all that metadata to find out which one maps, or is it like some in memory which you have, that you can hash it and immediately know which partition I need to go to.
Yeah, so all of the data that is needed to maintain, like to basically be able to restart and recover from failures, all of that data is persisted on the disk. But since this is common data, like, I mean, any queries to then index would go through the shards. This is common data. So this is always retained in memory. This is cached in memory by the Elasticsearch cluster nodes automatically.
And this index,
it's already
and
handled.
this index is same as the reverse index which we have, right?
Right.
So, hey, this is Ramesh. May I give you a little example here just to help the people folks here?
Sure.
So if say, if you're defining a user document, mentioning, username, and, age, and the gender, whatever it is. And if you have to mention their location, and you simply state their state name. So basically, when you're defining this user document, you're saying that my index is going to be my state, the state field, right? Sharding is actually takes Alabama, Alaska, Washington, Georgia, whatever it is. So within the, so you're mentioning that you're giving a structure saying that index is your state. Sharding actually picks those values and it vertically puts the data into different nodes. One node may have all the Alabama, Alaska, and the relevant corresponding state related data into one node. The other node will have the maybe all the states that starts with G or D, something like that. So when you issue a query, they ensure that all the nodes are working parallel to produce the data, and the results will be compiled back and sent to the user with the search. So in index as a whole, that's a logical partition. Sharding is actually the physical partition, how the data is co-located among the nodes, so that can be easily retrieved when you do the search. Abhilash, do it make sense? I mean, is it a right analogy?
Yeah, so there's a slight difference between the relational database shards and these shards, in the sense that in case of relational databases, we have to decide on what is the scheme we use for sharding. We can shard, let's say, based on data from, let's say, for each state, we have a different shard. So or for each type or for each value of a specific field, we have a separate shard. In this case, Elasticsearch handles how the documents are separated. So we don't have control over like saying that, okay, no, like we have this shard which has only documents that have this value for a field, but let's say for state of Washington, we have this shard. For state of California, we have another shard. So there's no way we can actually specify that this is how the sharding or split should happen. Elasticsearch randomly actually picks a subset of the documents and considers them as one shard, and picks another set of documents, considers them as another shard, and it can rebalance as and when needed based on the need. So if it feels, okay, no, this particular physical shard has a lot of documents and it needs to reduce them, it can move them to another node.
Okay, got it. So everything happens behind the scene without the user explicit specifications.
Right, and users don't have actual full control over how that sharding should happen, and they don't need to manually do it. Like they don't have to worry about it at all.
Okay, thank you.
But then in the schema file, we do have an option to tell what all fields we want to index. Moreover, that even contains a primary key, correct? So I think with the primary key, it decides how do we shard that particular list of documents. It's based on that primary key which you mentioned in the schema file.
So any fields that we specify in a document, okay, so the primary key, there's one ID field that is associated, which we can use to like create a document and but yeah, the mapping, even if a mapping does not exist at all, Elasticsearch is still able to like shard them based on the ID it automatically generates behind the scenes.
And is there a way to determine how many nodes or shards are needed for an use case?
So there are guidelines. There's no one right answer for this question. There are guidelines on how to do it. Like generally, it's recommended that a shard size shouldn't exceed like 20 to 40 GB. So like queries are efficient, but that's just a recommendation. It's better if the shard size is like within this range. It shouldn't be higher than that because then you might start to see problems. But again, it's just a guideline and could vary based on use case.
And a document could be part of multiple shards and multiple nodes also.
So one document will only exist, one unique document will only exist in one specific shard. So as I mentioned in my example, if there are 10,000 documents and there are 10 shards, each of the shard will have 1,000 documents. There's no overlap.
Yeah, I have a question, like how is it improving the performance? Like you mentioned, like we are dividing into 1,000 documents, 1,000 10 shards, right?
Yeah.
Having 1,000 documents. So like if the request is coming, then it will be searching in all the 10 shards, right?
Right. So a request came in and it wants to search in all 10 shards. If all of those 10,000 documents were in a single shard or a single node, then you have to go through all those 10,000 documents. So let's say you take 1 millisecond to go through each of those documents. Actually, it's going to be much less. Let's say you take 1 microsecond to go through each of the documents. Then it's going to take you 10,000 microseconds to go through all of the documents. Now, if you have 10 different shards, each of the shards would actually get the query, and they would execute that query independently on all the 1,000 documents in the shard. So it's taking 1,000 microseconds for each of the shards, but this computation is being done in parallel.
Yeah, okay.
And
Parallelism through it's improving the performance. Okay, got it.
right. So it's comparing 10,000 microseconds versus 1,000 microseconds plus the aggregation time.
Sure. Okay.
And then we have replica. Replica is basically a copy of a primary shard, and it helps maintain high availability. So this serves two purposes. One is like what if the primary shard has its data corrupted, or the node goes down, or there's a network issue on that node and it's not accessible. That data is always in replica, so we can actually recover from there. It also helps with serving read requests. So any queries that I perform, they could also happen on replicas. So they are all also available for querying. So if you're familiar with relational databases, a cluster can be compared to a database. A shard is comparable to a relational database shard as well. An index can be considered as a table. A document is a specific row within that table, and each field within that document corresponds to a column and its specific value. Any questions so far on this slide or this one?
Yeah, like can you explain what is this index to table mapping?
Okay. So in relational databases, you have a users table, right? You're storing, let's say, data of all the users. So you have 10 users. Each user has its user ID, username defined in separate rows, but it's a single table. That table is storing data for all users. So in Elasticsearch, we'll use an index for it. So we'll have a user index. Now this user index will have data for all users. So if we have 10 users, it will have 10 documents within that index.
Okay. So like a key value store, basically.
Right. So it's index is basically just a collection of documents, and there's one document per user in our use case. And similarly, in relational database, a table is a collection of users. Like the user table is a collection of users, and it has 10 rows, one for each user.
Okay. And what is the difference? I mean, I know you explained it earlier, but it was not very, can you explain it again about the sharding difference?
Okay, in a relational database, most of the relational database, they don't support sharding out of the box. So if you, let's say, use a SQL Server or MySQL, it doesn't come with a sharding capability. So all sharding is built on top of it, like by using some external tool or doing something manually. So how do we do it? There are several mechanisms we can shard data. There are several mechanisms we can shard or divide data or partition that data across different machines. So if you think, okay, database size is growing, I want to split this across multiple machines, then I have to come up with a scheme. How do I divide that data? So I have this, let's say 100 GB of data in the database. How do I divide it across multiple nodes? I could say that, okay, like I might store a subset of the tables in one. Let's say I'll store one table on one node, let's say user table on one node, products table on another node, and so on. This is one way to do it, but there are lots of other mechanisms to do it as well. So this needs to be done on top of it by, like, on our own. We have to define how that data is being divided across nodes. In case of Elasticsearch, um, the sharding mechanism is not based on any of these specific mechanisms. It's automatically handled by Elasticsearch randomly. It just randomly picks up a subset of the documents and then divides them across different instances. Why is it able to do that? Because any queries that are executed are distributed across all shards, and it doesn't matter for Elasticsearch queries to like be able to separate, okay, no, this is the shard I want to go to. There's no immediate benefit. So there are ways to do it as well. Like even in Elasticsearch, you can have queries that say that, okay, I don't want my query to go to all the shards. I want my query to only go to a specific shard because I know that is where the data resides. But again, like that's all handled by Elasticsearch, although we have some control in some ways, but it's slightly different from relational because it's being handled out of the box. So you can compare it to the shard and NoSQL relational databases like DynamoDB or Cosmos DB. I think that there are more similarities.
Yeah, makes sense. Okay. Thanks.
Yeah. Okay, so this is the last slide I have. This has a pictorial representation of how the primary and replica shards could be stored across nodes. So this entire box is represents an Elasticsearch cluster. This specific example has 3 nodes. These nodes, each node, think of it as it's hosted on a separate physical machine. It's possible to have them on one machine as well, but like the recommendation is to have them on separate machines to get all the benefits. The white box, the primary 1, primary 2, and primary 3, these are actually primary shards. So what I'm saying is, let's say I have 3,000 documents in my entire index, and each of the primary shards has 1,000 of those documents. And primary one has 2 replicas. Okay, so then there are replicas. So the primary one has 2 replicas, replica 1 in node 2 and replica 1 in node 3. The primary 2 has 2 replicas, replica 2 in node 1 and replica 2 in node 3. And it's the same case for primary 3 as well. So you can see if the primary shard is on one node, its replicas are stored on other nodes. So if one node goes down, we always make sure that we have the replicas available in case we need to access. And the management of these shards, where the shards are stored, where the primary shards are stored, and where the replica shards are stored, all this management is being handled by Elasticsearch out of the box. Any questions on this slide?
Can you explain one like fault scenario and the like query flow?
Sure. So a query comes to Elasticsearch cluster at a specific index. Now there can be different types of queries. So let's say we are querying at the index level. Now that index has 3 shards. Let's say primary 1, 2, and 3. It has 3 shards. The query is sent to all of these 3 shards, because each of the shards has different, like, unique set of documents. So we need to aggregate results from all of these 3 shards. So that query is divided across all of these 3. Each of the individual shards is actually a single Lucene index, as we already discussed. So this executes that query on that Lucene index and computes the results. So each shard has its own query results. And then those results are actually aggregated and returned. So there are other nodes there are lots of other nodes actually that this picture doesn't show. So Elasticsearch cluster will have a master node, which will be taking the query and distributing it across the shards, combining the results, aggregating them, aggregating those results, and then sending the result back. And let's say if primary 1 goes down, then the master node knows that primary 1 is no longer available. So it will send the request to replica 1, primary 2, and primary 3, get the results, aggregate them, and return them. And besides the master node as well, there are actually client nodes. So the master node is actually not aggregating, just to correct. There are client nodes that actually do the aggregation, and master node is used for cluster management. And there are a few other nodes. So we won't have time to actually go into like all the different kinds of nodes we have. But let's say if for this specific slide, if one of the primary ones is down, the client node knows that it needs to call the replica instead. So it will make that query to the replica, combine the results from replica 1, primary 2, primary 3 in this case. Does that answer your question?
Yeah, that's fine.
So we have a concept of key node, data node here, right? Similar. Okay.
Yeah, so we have we have several different kinds of nodes. So let me quickly go through the questions in the chat just to make sure we're not missing them. How are duplicates resolved when multiple shards return duplicate results? So each shard has a unique documents, unique set of documents. There's no overlap of documents within each of the shards. So any duplicate results are actually separate results that need to be shown in the query. Then Ayush has asked any use case for understanding shard significance. So so the data within an index, so there's no limit on how much data we can store in an index. It could have a large set of documents. So we need to divide them in some way. Because let's say if I have 1 million documents, I can't store all of them in the same node, because node has its physical limitations. It has limited memory, disk space, and so on. So a shard is basically a concept that we are using to divide that data and make sure we can effectively balance that data, like replicate that data across different nodes, as well as like a shard can be limited to a subset of the documents enough so that the current memory and disk space requirements are like generous enough. So let's say if I think that one specific node can only handle queries to a certain extent, like because of limited CPU and memory available, I will only limit that shard to a certain number of documents, because if there are more documents added, my queries would get slower. So that's why I need more shards in that case. So that's the benefit we get from shards. Then Shashank has asked, is collection similar to collection, which is in MongoDB? I'm not sure what collection refers to here. Shashank, are you on the call?
Yeah, I was saying like in MongoDB we have each row, right? And each what is a collection refers to the what is it? You collect all the documents and put it into one separate collection. I think which AJ has cleared it somewhere in the chat. The collection in the start, I mean Elasticsearch, which is equal to your table in the RDMS, right? I mean your collection will have many docs, isn't it? In MongoDB, the NoSQL database, right?
Yeah, so collection, I'm guessing, so I'm not familiar with MongoDB, but I'm guessing it's
That's correct. Yeah.
strict partition, right? It's like a partition, like you can exactly know where the data resides in a collection. So I would compare it to an index, probably.
Sure. Yeah. Thanks.
So
I have one question. So in this Elasticsearch cluster, you have like primary nodes and you have replicas. So so this primary node is used for like doing like write requests, and the replicas will be like used for read requests, and all the writes will be replicated to each of the replicas. Is it like that? That way?
yeah, that's correct. So reads are served by both primary shards and the replica shards, and then the writes happen on the primary shards, and then they're propagated to the replicas.
So like if the primary one goes down, so it will be same like that leader follower. So another replica will become like a primary, and then it will continue to function the same way. Is it that way?
Yeah.
Okay. Yeah, just wanted to.
And then Shashank has another question. So Elasticsearch falls under category of NoSQL databases. So yes, it's a NoSQL database. Okay, and then Ayush has a question. Any use case where Elasticsearch cluster should be put in Kubernetes cluster? Will it increase complexity in design? So Kubernetes is a container orchestration platform. And with Elasticsearch, you already have nodes that are managing all these indexes and all the nodes in the cluster. So I would consider it as completely separate. It's already a managed set of nodes.
But to answer that, yeah, we did it like in the like we set up a Elastic cluster in the Kubernetes cluster, and yeah, we did it.
So
But
you can actually keep that in a Docker image and use that. But internally, as a where you keep it, how you use the Kubernetes and Docker is different. Elastic itself
yeah, it's a
manages
separate
itself.
function. Yeah.
Yeah, Elastic itself can manage itself, but where you keep that is up to your team's implementation.
Yeah, we can keep it in Docker or Kubernetes. Anything is fine.
Yeah.
Yeah.
In our team, we use Docker, install different parts of Logstash in Kubernetes, and in a specified Docker images. But you don't need to. But for scalability and ease of different, your application might be different, so you can use that.
Yeah, and then Raja has a question. How does it handle multiple indexes? So each index will have its own primary and replica shards. So for an index, we can define, okay, I need these many primary shards, and I need like these many replicas for each primary shard. So we can actually, the next step, so this is the last slide we have, we can actually go and actually check out queries on how we can execute queries on Elasticsearch. Like we can have a demo of that as well. Like I think we have 9 minutes left until 10:30. So Sukhbir has a question. When we do a query on Elasticsearch, how do Elasticsearch figure out which index is best for that query to get the results. So these indexes, okay, I think there might be some confusion on what an index is. An index here is the primary source of data here. It's comparable to a table. And it has associated pre-computed data. So what that index has is it has the actual data as well as the pre-computed data. Basically, it has pre-computed data that will help you to perform all those complex queries. So when you query, Elasticsearch cluster, you can do a query across all indices that exist, or you can pick a specific index. So if you pick the specific index, then it knows which index it needs to send the query to. If you picked all indexes, then it's going to send the query to all the indexes and then aggregate the results from there. Does that answer the question?
Yes, yes.
Okay, so let's see if we have a few minutes to actually check out queries on Elasticsearch cluster. All right, so this is the REST API documentation for Elasticsearch. As you can see, there are a lot of different categories of APIs. Some of the ones that I'll quickly go through, like one is the cluster APIs. The cluster APIs, you can see, you can get nodes, all the nodes that exist in the cluster. You can get the local nodes that exist in the cluster. You can get the master nodes that exist in a cluster. You can get nodes by a specific name or a specific pattern or by a specific address. So there are lots of ways to actually query the nodes that exist in the cluster using the cluster APIs. The next set of APIs is the document APIs. The document APIs you can use to index a document. So indexing a document means to add a new document to the index. And you can get an existing document. You can delete an existing document and you can update the fields within an existing document. There are other APIs that you can actually get multiple documents at once. You can perform lots of combination of the queries that we already talked about above. You can delete documents that match a specific query, update documents that match a specific query. You can reindex that data, all that data differently, maybe after adding additional mappings. Then there are index APIs. So index APIs help you manage the indexes, the mappings, and the aliases associated with them. So you can create, delete, get, and modify any of the indexes. You can check if they exist, you can clone them, and there are lots of other operations that you can do. We have a set of APIs to manage the mappings that we talked about. Alias is the concept we haven't discussed, but it's just a different name to refer to an index. And then we have some APIs. Okay, the search APIs are interesting. The search APIs are the ones we'll use the most. In general, we can perform all the different kinds of searches that exist. So if I click on, let's say, search, you can see I can have my index name, and then I can use the _search API, send a GET request to it, and get results for it. And just to have an example of certain queries, so this is the demo environment. You could go to demo.elastic.co to perform queries on in a sandbox environment. This is the sandbox environment provided by Elastic. So let's say I can execute get _cat/indices query to see all the indexes that we have available. We can, so this has autocomplete as well. So this is the DevTools environment. After I went to demo.elastic.co, I can search in a specific index as well. So let's say I did this, and then I want to see, okay, these are all the indexes that currently exist. So let me just pick this as the index name, and I want to perform a search query on it. So let's say I want to get all the results. So I can just execute this query. And then this is the result I got. So if you see, this query took 25 milliseconds to execute. This query did not time out. This returns the shards. Like, so there were a total of 118 shards for this specific index. The query was successfully executed on all 118 shards. No shard was skipped and no shard had a failure. Hits corresponds to the results. This means that there were more than, greater than or equal to 10,000 documents that matched the query. So my query was basically, it did not have any filters. So it returned all documents. And there's a limit set in the settings to limit it to 10,000. So it means that they were greater than or equal to 10,000 documents that matched. Score is something that is assigned by the Lucene library based on how good of a match this document is. So in this case, each document has a score of 1 because we are fetching all documents. But if we were doing a fuzzy search, then it would fetch a subset of the documents, and each document will have a different score. Hits has all of the results. So you can see if I collapse these, hits has all of the results. So there will be 10,000 such results. In this console, there might be a limit because this is just a demo console, but you can see in each of the results, we have metadata fields that start with an underscore. So this means this is the name of the index. The type of this index is actually underscore doc. This is the ID of the index, which was automatically generated by Elasticsearch. Score is 1.0 because there were no filters and this matched perfectly. Underscore source is the actual document that was stored. So this is the JSON object, actual document that was stored, all of this. So these are logs, some file beat logs, basically beats logs from one of the containers. And you can see it has all the fields. I'm not sure we have time to actually try different queries and actually see how that filtering mechanism works.
So Abhilash, we generally have session till 11. If you have time, you can extend. But if you have a hard stop at 10:30, we can wrap it up.
Okay, I guess then, yeah, we could continue. I kind of thought like it was the stop at 10:30. So this is, okay, then we'll probably go a bit more into the APIs. Let's look at the cluster APIs. So, so when we're referring to clusters, we so we can use underscore all in any of the APIs to refer to all of that type. Like let's say underscore all in cluster APIs would mean all clusters would receive that request and process it. And for search APIs, if I'm using underscore all, it will refer to all indices. Yeah. Question? Okay. If we refer to underscore local, the request would be sent to only the local nodes in the subset. Local basically means the non-master nodes, and we could use underscore master to send the request to all master nodes. So this is for management of the clusters. If you want to see what the health of the cluster is and what is the metadata associated with each of the clusters. So if I go back here, I can say underscore get. I can get all the commands here. So let me give a brief introduction of what this is like. So I go to demo.elastic.com, and then from the left pane that I get, I scroll down and go to DevTools. So this is how I arrived at this page. I go to demo.elastic.co, and then I open this navigation bar and went down to DevTools. So DevTools allows me to execute Elasticsearch queries on the cluster. And there are other ways, there are lots of other tools that it provides. So it has Kibana. I can actually perform lots of queries on the data. And I can use, let's say, stack management to see all the indices that exist and manage them, like when they were created, what is the size of those indices, and so on. So DevTools will help us do all of those queries. This is a pretty cool interface, supports autocomplete, returns lots of results, and I can press like control space to actually see the list of all commands, and it shows me what these things are. So you see .kibana event log 7.10.0. This is actually an index, and then I can scroll down and see all the indices that currently exist. You can see underscore alias, it says it's an endpoint. So I can search for all the aliases or like different names assigned to the indices. These are all endpoints, like underscore cat ones. You can get all the indices, you can get the health of the cluster. So not all of these commands you can execute in the sandbox environment because it's pretty limited. But if you set up Elasticsearch locally on your own machine, then you can query all of these commands and see the results. So you can also query, let's say, all the shards that currently exist and get metadata for those. You can get cluster allocation statistics. You can modify the settings there. You can get all the mappings that are existing for any of the documents. So the endpoints, you can see you can use the search endpoints to perform any of the searches, which is what we use to list all the documents. Again, these are all the endpoints. These are indices. And there are a lot of them for to test things out. So for our case, we picked up this specific index, and we were basically using underscore search to list all the documents. We did talk about these fields, so let's go into detail of the other fields. Hits. So each of the results in, okay, so this specific query matched greater than equal to 10,000 documents. So hits is a collection of these documents. In one of the documents, in each document, you'll see certain fields that start with an underscore. So this means that these are fields that are basically the metadata about the documents in general. Like underscore index means the like what index it came from. This if you see this index name and the index we actually search for are different. So this like filebeat -7.10.0 is actually an alias created to point to the most recent index. So, and this index you see, this has a specific date, which is like this date, 25th of March, 2021. So we have logs from beats being created for different times, and this alias is being used to point to one of these indexes. So we can say that, okay, we have user data being generated, user logs being generated every day, but we have an alias which points to the logs for the most recent day. And underscore type is used to just like filter out the type of documents. Now within the recent Elasticsearch versions, the type is going to be the same. There's only going to be one type of document within an index. And underscore ID, again, random like unique identifier generated by Elasticsearch. Source is the actual document. So let me collapse this to see what kind of fields we are logging in this index. And okay, a lot of fields. Yeah. And as you could see, the value for each of the fields could themselves be an object and a complex type. So let me try one sample query. This field has an ID, and this field each has a different ID. Let me scroll down a bit and pick a document. ID. So this is the ID that I picked up. Let me just copy it. I can add additional query parameters to the search. So I can say my underscore ID field is actually this. Only query these documents where underscore ID field matches this, and execute the request. So now you can see this query took 2,605 milliseconds. So the time it's taking here would vary drastically across runs, because this is again a sandbox environment. But in general, you can see what's the status code for the request, how much time it took from the client side, how much time it took on the server side. And in this case, the request went to, again, all 118 shards. All of them returned a successful result. There was only one hit. So the number of matching documents was equal to 1, and max score was 1. So this is the matching hit we got. You can see it's a single hit. There are no other documents returned. And the ID of this document actually matches the one I passed. So this is one way of querying, but there are other ways of querying as well. So let's say I remove this. So I can pass query parameters in the URL, or I can just pass them in the body as well. For the body, this is a very specific query syntax that it supports. So if you look at the search APIs, you can see there are lots of query parameters. So these can be used to pass filters and query parameters in the request. There are also request body parameters, which you can pass in the body of the request. So for an example, one of the examples I have is I can say that query parameter matches a specific field. Let's say I'm saying, give me logs, show me the documents for all the, okay, show me those documents which have, let's say, service.type field or something. Let me see what the service.type is. So service.type is just an entry within the document. This is the service. So this is a document. This has the service. This has the type as Apache. So let's say I want to get, so I can use the dot notation. So I know the top level object in underscore source is service, and inside it has a type. So I can say service.type matches, let's say, Apache, and then run the query. So it's going to give me all the documents where in the underscore source field, the service.type equals Apache. So I can see I had more than 10,000 matches in this case. And all of these hits will have the service.type as Apache. And I can change it as well. So if I want, let's say, service.type as Redis, I can execute the query, and I can see, again, there are more than 10,000 matches. And this time the documents that have been returned have service.type as Redis. So any questions so far?
This 10,000 document is basically the offset, right? The limit what we want for the number of data points to return.
Right. So 10,000 limit is enforced by default because there may be millions of documents and we don't want like too many documents to be returned. But this will return the exact number of documents that matched if that limit is below the max limit set.
Here the ID is unique and the index is not unique, right?
So index is similar to just the name of the table. So that table will have a lot of documents, and ID is the unique identifier to identify that document within this index.
Okay, got it.
So I have one question, Abhilash. So in the query format that you shared, if I want to, instead of doing exact match with Apache, I want to search for, let's say, Apache Lucene, and wherever the Apache keyword appears, in the document, will that return those results as well? Like if I just want to do prefix match or lowercase, uppercase, all these kind of queries, how does Elasticsearch handle that?
Yeah, so Elasticsearch supports tons of different queries. So you can say like whatever results. So, and you can actually use request body and parameters at the same time as well. So let's say we have 10,000 documents here. You add a query saying that only give me all only show me the results which have, let's say, um, um, let's say SHA-256 in the query. I can just click on it. Okay, it actually didn't find any. Let's say I type Apache in the query. It did find lots of results. And let's see where Apache is actually. See, this Apache was in the middle of a message. So it's basically searching every field and every value, like anywhere in the document.
Does that need to be an exact match in terms of casing as well? Like if it's an uppercase Apache, would that still return the same?
Yeah, see, I executed this and it's still matched. And I'm pretty sure there's no document which has P capital in the Apache.
Got it. So probably that's where the score will come in, because I also had question, how does the score is relevant? How do people use score in the in the use cases? The score field that is written by Elasticsearch.
Right, yeah. So based on the query and how good of a match each of the documents is, a score would be assigned. And this is handled by the Lucene library itself. Apache Lucene handles it. And Elasticsearch is consuming that library to determine that.
Got it, thanks.
Any other questions? Okay, so let me just share a little more complex query that I tried initially and just run it. Okay, so there are lots of ways to actually query, and one of these is, let's say I'm specifying that, okay, this is my query with a Boolean result. The query, I want to match, I want to find documents that satisfy this criteria, but they don't match this criteria. So what this is saying that give me all documents where this is the process.pid. Give me all those documents also should have log.offset as with this specific value, but those documents must not match this specific query. And this is like must and must not. You can also specify, let's say, should or should not, in the sense that those won't be hard filters, but they would reduce the score. So if I specify these two as should, so if you see this query has only one hit because there was only one such document which satisfied all of these three criteria. So in case these were changed into, let's say, should queries, then I'll have a lot more documents, and the ones that match will have, ones that completely match will have higher score, and the other ones will have lower score. And just to give you an idea of all the different kinds of some complex queries, like this is a useful page to reference. Like it's the dzone website. It has some good examples on the kind of queries you can make, like the basic query match. This basic query match is what we actually tried. So in the books DB index, it's actually searching documents of type book and then searching. So this is where type is useful. So this documentation is using the old format where we used to specify the type in the query as well, but you can always skip it as well. Like this is optional. You're searching all the book documents for a string named guide. And this is returning all those hits. So this is the simple search, a basic query that we already tried. You can also have multi-match queries where you can specify like some complex criteria on like multiple fields or like multiple values for a field. And this one also we tried, like we are specifying that this specific field should have this specific value. And there are other types of queries that are supported as well. Queries for boosting, these are Boolean queries, which we already saw. Queries related to wildcards, like star and question mark, like both of these wildcards are supported. You can also specify like regular expression queries, like instead of full match or prefix match, you can specify that, okay, the author's field should match this regex, only get me those documents where this regex is satisfied. We also have a few different kinds of queries, as you can see, and different ways of expressing those queries. Term queries, there are a ton of them, and all of these are like supported by the Lucene library. You see range queries, let's say date is between like a specific set of dates, and so on. So yeah, see, it has a ton of different kinds of queries that you can use. And so it's worth trying. Like just go to demo.elastic.go, click on the navigation bar, go to DevTools, and try out a few queries just to familiarize yourself with it. So we've gone through cluster APIs, which help you get the state of the cluster and the state of the different nodes. We've also tried out a few search APIs. Let's look at the document APIs. Let's say bulk. You can specify that, okay, run all these queries. Like I want to index a specific piece of data. Let's say this is creating a document, and this is deleting a specific document, and so on. This is updating an existing doc with this ID. And I can specify it's like a batch request. Similarly, let's say pick one of the APIs. Let's say update. I can specify this is the index, and I want to update a document within that index, and that document has a specific ID. So I'm actually targeting a specific document using the underscore ID field and then updating those. And again, you can use the REST API documentation to see all the supported parameters. There are a lot of them. And there are pretty good examples of these as well. So let's say you can say, hey, this is my index name. This is the type. And this is the document underscore ID value. And you're updating its value, updating the document with updating these specific fields in the document. And this is actually updating the complete document underscore update. So you can see examples on this website. There are a lot of them. So we won't be going through like most of these actually, but I think we have had a chance to actually look at least one of the few of the common ones that are used. So REST API documentation is one I would suggest referencing, and trying out the sandbox and trying out some of these queries like from dzone. Those would be the good next steps. Any questions so far?
No, I think.
Okay, let me check if there are any questions in the chat. Okay, no. Okay, so since we have a little more time, let's go look at Kibana. So in the initial slides, we talked about Logstash, Elasticsearch, and Kibana. And Kibana we mentioned as like it helps us like analyze and visualize our data. So this is the way we can actually see we can query the logs. So these are all the logs being published to Elasticsearch. Kibana is actually querying Elasticsearch and allowing us to execute queries using a different language. So we already looked at some of the APIs that Elasticsearch provides to query the clusters and indexes directly. This one allows us to use two different languages. So one is the Kibana query language, which is like much simpler than the weird syntaxes, like these kind of ways of like querying, which could be harder sometimes. The Kibana query language is a much simpler way, and you can always turn it off if you directly want to use the Lucene language to query. So let's try a Kibana query language. So these are our log fields. You can see the timestamp. You can see the underscore source field that we saw in the Elasticsearch document. You can click here and see the individual fields. These are all the individual fields. And if you want to see the full document, you can click on the JSON. And this is the Elasticsearch document that this line in the logs corresponds to. And you can customize the view. Let's say I don't want to see underscore source. I only want to see, let's say, the container ID field. And let's say I have some maybe log field. Let's see if it's there. Okay, basically you can select what kind of values you need, and it will only show those values from those documents, or you could show the entire of them. Now, let's say I click on this, and I want to find all logs, which are, let's say, errors. I want to find all errors. There are multiple ways to do it. Kibana query language makes things very simpler. I can just type error, press enter. It also has like auto suggest for all the different fields and like the queries we can use. So I don't need to remember the syntax. And this is the timeline I'm setting. Query all the logs in the last 15 minutes. So I'm just going to collapse this and click on update. You can see this. This means that it's in progress. And now my query has been filtered to show only the errors. And this is the visualization. So for the last 15 minutes, it's basically building a chart of how many errors were there. So you can see there was a surge in error count at these two times. I can even click on this and it will filter you see the timeline is now, the duration is now updated, and it filtered the results. And I'm basically drilling down that time and then looking at the entries. So this is a very quick way to search, like it searches all the fields. But I may say that, okay, let me just check the logs, and this is the container name. These are all the fields being used. This is the host IP. This is the host name. Let me filter down to all log entries that have this specific host name. So I can specify, say, host dot name matches, let's say this. I can press enter, and you see it now just reduced it to just these 4 hits, because for this specific host there were only 4 errors in this time duration. So now I can just analyze that. So it makes querying a lot simpler, as so I don't need to like construct those complex queries in Elasticsearch. I can easily do that here. And Kibana also provides the ability to build dashboards out of it. So I can use these queries to construct dashboards. I can do lots of aggregation, like count of data, summarization of data, group by separate data, and do some filtering, and then build a dashboard to get all of this data processed in near real time. So that's pretty cool. Any questions so far? I think that's all we have for today's session. So we can spend the remaining 3 minutes in questions.
So yeah, this Kibana is nothing but it's just like simply using the API from Elasticsearch, right?
Right. Yeah. So Kibana is just translating your queries from either the Kibana query language or Lucene, and then executing them on the Elasticsearch cluster.
So the way this dashboard you're presenting is working, it seems something similar to GCP dashboard for logs, right? So is that we can just resemble that way how it's working?
Yeah. So this is not the dashboard. The dashboards are actually separate. If I click on this dashboard link, I can actually build lots of dashboards. So Elastic has some examples, I believe. Like some of these like dashboards exist. Let me just click on any of those. Okay, so this is a different one. But yeah, dashboards are similar to what you do in Grafana. You can pick, like you can build like charts, any kind of charts. There are a lot of different supported charts to analyze the trends. So you look at some of these charts. Let's say this one. This in the background is executing a query which is internally using the Elasticsearch REST APIs. So any graph any kind of like graph or chart you want to analyze or summarize the data from the logs, you can build a dashboard out of it. The one that is shown here, this one is just like to help you see like how those logs are distributed. Any other questions? All right, thanks everyone for attending. If you do have any questions, like feel free to send a message on our Discord channel. Thanks everyone.
I have one question about the logistics. So when will be the next section, like algorithm or anything?
Sorry?
When will be the next session for algorithms or system design?
I would stop the recording and then we can continue the discussion. But thank you so much, Abhilash, for this session. This is really helpful for anybody who is going to attempt system design interview and want to use Elasticsearch. So yeah, really appreciate that. Thank you.
Thanks, Abhilash. It